20th century, limnologists in Scotland modified and deployed lake-level recorders, or limnographs, based on designs used by François-Alphonse Forel in his founding studies at Lake Geneva. These detailed observations showed that the long, narrow locks of Scotland provided excellent examples of the wind-induced periodic fluctuations in lake level, called seiches, that had captured Forel's attention. At Loch Earn in the Southern Highlands, Ernest M. Wedderburn and his colleagues from Edinburgh extended this work by taking detailed temperature profiles in late summer. It discovered that the variations in wind velocity induced much larger waves across the thermocline, the internal seiche, with complex patterns of undulation and mixing. Today, in recognition of this classic work at Loch Earn, Wedderburn's name is given to a key index, the Wedderburn number with the symbol W, which is used by limnologists to estimate the extent of thermocline tilting and the likelihood of mixing between the layers of a lake. This layering and the mixing of a lake over daily, seasonal, and annual periods is the result of heating and cooling of the water combined with the action of wind on the water surface. Surface heating over summer results in a reduction of density near the surface, producing an upper layer, the epilimnion, overlying the cold, denser waters of the hyperlimnion. These two layers are separated by the metalimnion, also known as the seasonal thermocline, where temperature changes more rapidly. Detailed temperature profiling of a lake, for example at centimeter intervals with a conductivity temperature depth profiler, or CTD, can reveal that the epilimnion is composed of sublayers, an actively mixing layer, a temporary near surface or diurnal thermocline, and a subsurface layer. The hyperlimnion is also sometimes divided into sublayers. A near bottom one, called the bottom or benthic boundary layer, where stratification is weaker and more mixing occurs, and a quiescent layer above, where stratification is slightly stronger. Annual cycles of heating and cooling in lakes demonstrate patterns dependent on latitude, local climate, optical conditions, and lake depth. For example, a small shallow lake in Michigan, studied by Bob Wetzel in the 1960s, was ice-covered from December through March. Water density increases over the range 0 to 4 degrees, and therefore during this winter period, Lawrence Lake exhibited so-called inverse stratification. That is, water temperature increased with depth. The coldest water was immediately under the ice and overlaid warmer water, which was denser over this temperature range. Following ice-off, temperatures were nearly isothermal at 4 degrees, the temperature around the maximum density of fresh water. And temperatures then rose with increased solar radiation entering the water, and thermal stratification developed by May, with several periods of heating and cooling over summer. By August, as incoming solar radiation declined, the mixed layer began to deepen, and the lake was isothermal by November. This period is called fall turnover. With near-surface temperatures cooling, the water near the surface becomes denser and causes convective mixing to the bottom of the lake. More recent work has shown that during both spring and fall turnover, the wind induces large internal waves that contribute to the mixing. Ice-on occurred when temperatures in much of the water column had declined to 3 degrees and were near zero at the surface. Lakes with this annual pattern of stratification, or layering, and mixing, with 2 periods of overturn, are called dimictic. These are commonly found in regions with warm summers and cold winters, but several other patterns are also found throughout the world. Many deep lakes in warmer regions have a single period of prolonged mixing each year, for example here at Lake Geneva on the border of Switzerland and France. The African Great Lake, Lake Victoria, is another example of a monomictic lake with a single period of circulation each year. This mixing occurs during the southeast monsoon when winds are higher over East Africa. These lakes are called warm monomictic, with the mixing taking place after several months of warm stratification. In high latitude regions, cold monomictic lakes can be found, in which convective mixing takes place in summer after the cold months of ice cover and inverse stratification. A classic example is Char Lake in the Canadian high Arctic, here based on observations in the 1970s. More recent observations of this and certain other lakes in the Arctic indicate that with climate warming, these lakes now stratify in summer and are now dimictic. Toolik Lake, Alaska is a well-known dimictic Arctic lake with mixing in fall and spring overturn at ice-off.
Hi, my name is Sally McIntyre. I'm a professor at UC Santa Barbara. Behind me you see a water body. And I'm going to flip this and you can see it. Okay, the inlet, Toolik Inlet, is just right here, and there's not a lot of water flowing in right now. And we call this the Inlet Bay. It snowed this morning. It's the 9th of July, but it is the Arctic. Right? So you can see a little bit of snow there on Jade Mountain. And of course we have 24 hours of sunlight up here, and it's about 10 o'clock at night. So this is just a small bit of the lake for you to see. But I've come up here to look at the physical processes that moderate nutrient supply to phytoplankton, light supply of phytoplankton, and to do that requires understanding lake physics and also studying the fate of heat, since that's what causes the stratification.
Meromictic lakes are another group of water bodies that occur commonly in the polar regions, as well as elsewhere. These are partially mixed, in that their surface waters may lose their ice and mix in late summer, but their bottom water columns are continuously stratified by dense saline water. Finally, polymictic lakes mix several times each year. An example is this large, shallow, windswept lake, Lake Rotorua, on the central volcanic plateau of the North Island of New Zealand. The thermal structure of lakes is determined by the fluxes of energy across the air-water interface, sediment-water interface, and incoming water as it mixes with the lake, along with the action of wind. The fluxes across the air-water interface are quantified via a surface energy budget, computed from time series measurements of meteorology and water temperature. These surface fluxes are generally the largest source of heating and cooling within a lake, and can be summed to calculate H, the net surface heat flux, in watts per square meter.
Sally McIntyre again, here on Toolik Lake. And my goal now is to show you the vet station on Toolik Lake. This is put out every year by the Arctic Long-Term Ecological Research Project. I'll turn my head and point. At the very top, you might actually be able to see the anemometer spinning, and there's a wind vane on the other side. Below it, we have it set shielded air temperature and relative humidity. Sticking out over the lake is instrumentation for measuring downwelling shortwave and longwave radiation, and then coming up from the lake, shortwave and longwave radiation. You might just be able to see a blue float in the water, and suspended from that is actually a thermistor array.
The thermal structure of a lake over an annual cycle is related to its surface energy budget. For North Temperate Lake Mendota, Wisconsin, net radiative heating begins in January and peaks in July. Since the lake is cold following ice-off, conduction is initially positive as air temperature is warmer than the surface water temperature. Conduction becomes negative, that is, loss of heat from the lake, in summer as the lake continues to warm. Evaporation becomes a progressively larger heat loss term as the lake's surface water temperature warms. And the sum of these terms, the net heat flux, indicates whether the lake is gaining or losing heat, and this flux becomes negative by late summer. Vertical mixing redistributes the heat introduced at a lake's surface, as well as any solutes or particles that are not uniformly distributed. Were it not for this mixing, temperature profiles would follow those of irradiance, Instead, lakes have more complex temperature profiles. The downward mixing of heat, the flux, is conceptualized as the product of a coefficient of eddy diffusivity, Kz, and the temperature gradient, multiplied by specific heat capacity and the density of water to convert temperature to heat. Kz represents the product of the average size of turbulent eddies multiplied by their average velocity. This process is analogous to molecular diffusion, but often several orders of magnitude faster. Wind-driven mixing can not only distribute heat and materials throughout the surface mix layer, but if intense, may also act across and erode the diurnal or seasonal thermoclines. A number of indices have been developed that measure the stability of the water column and its potential resistance or response to wind-induced mixing. Schmidt stability expresses the amount of work, force times distance, required to mix the lake completely, and it is calculated by summing the density layers weighted by their distance to the center of gravity of the lake. Buoyancy frequency, N or Brunt-Väisälä frequency, is used by oceanographers and limnologists to identify stable layers and the strength of stratification in the water column. The Wedderburn number, W, named after the Scottish researcher Ernest Wedderburn, expresses the ratio of the tendency of the lake to resist mixing, determined by the density difference across the thermocline and the depth of the upper mix layer, to the tendency of the lake to mix, determined by the water friction velocity, U star, computed from wind speed, and the length of the lake, L. When values of this dimensionless number W are high, there is no tilting of the thermocline. At moderate W values, partial tilting occurs. At W values around 1, full upwelling occurs, while very low W values, much less than 1, indicate conditions of complete mixing. The lake number, Ln, provides a similar perspective as W, but takes into account the morphometry of the entire lake. It expresses stability in terms of the Schmidt index and wind stress in terms of friction velocity and lake surface area. The consequences of a low Wedderburn or lake number vary during the ice-free stratified period. During spring or early summer, wind events strong enough to cause these indices to drop below 1 cause the mixing of heat downwards and often thickening the thermocline. During midsummer, the thermocline abruptly descends, and in late summer, the thermocline is eroded. In this example from Toolik Lake, Alaska, the time series began immediately after ice-off. The epilimnion stratified in the day when skies were sunny and winds were low, and mixed when the winds rose and heat was lost at night, or during the passage of cold fronts. The time series of Ln showed periods when the wind was high enough relative to stratification to cause mixing across the thermocline, and exchange between the epilimnion and hyperlimnion. The thermocline, indicated by maximum N values, descended in early summer from days 180 to 210, and then remained at relatively constant depth over the subsequent month, days 210 to 240. Stratification ended with the combination of a cold front and winds reaching 10 meters per second, and decreased Ln values falling to 10 to the minus 2 in early September. The associated mixing event was so intense that it caused the thermocline to descend from 11 to 19 meters in just 3 days. Climate change is having multiple effects on lakes associated with the warming of surface waters. Later onset and earlier loss of seasonal ice cover, longer periods of stratification, and reduced mixing of surface with bottom waters. These changes are triggering an array of biological and biogeochemical processes. notably a greater loss of dissolved oxygen from bottom waters due to reduced mixing, with cascading impacts on nutrient supply and on fluxes of methane and other greenhouse gases.